Welcome to Sound Learning, to our last presentation for the year. This one is on the Hubble Telescope, and so let's begin. So what we've got coming is the Hubble. Talk about what the Hubble itself was. Why are we using it in space? Why did we put it in space? And then we're going to address who Erwin Hubble was and why is he important and why he got his name on this telescope. Well, then we'll have some Hubble images. We'll look at how the solar system was created and the Hubble verified that's how it was happening. And finally, we're going to create some elements, parts of the periodic table in this discussion. Finally, the moons for the various planets, how they're created, and lastly, life in the universe. Is there life out there? So who am I? Well, I have a degree in physics. I've attended classes at FGCU. I was a principal engineer at Perkin-Elmer, and I worked on the Hubble telescope design team, primarily on the fine guidance system. I also have some optics that are currently flying on the International Space Station. I consider myself to be an engineering physicist. By that, my first job was in measurement standards while we were building the Atlas and the Centaur rockets out in California. In some cases, we were certifying the instruments used to make those rockets to a millionth of an inch. So let's take a look at what overall NASA wanted to do. They wanted to create 4 great observatories that would cover the entire spectrum of interest. So those telescopes started with the SIRTA, which is a space infrared telescope facility, which would cover the long wavelength IR. The Hubble covered the visible portion of the spectrum. Chandra looked at the X-rays that were coming out of space. And finally, the Compton Gamma Ray Observatory looked at the very, very short waves that were out at the far end of the spectrum. So what is the Hubble? It's a spacecraft telescope combined, which was launched in 1990. It's currently located 300 miles above the Earth. It does an orbit every 97 minutes. Designed to work for 15 years, it's now functioning in its 31st year. So it's really outlived its life and still going strong. It weighs 25,000 pounds, 43 feet long, has incredible resolution of 24,000 times better than the human eye. And finally, it can guide on an object as small as a human hair 3 miles away. So this is a NASA slide, and a lot of NASA visitors are school kids. So they related the Hubble to a school bus. And you can see they're comparable in size. They're both in the 44-foot range and roughly the same diameter. So last year, this cartoon circulated among some of us who worked on the Hubble, and it was all in good fun and a nice chuckle to see this cartoon come up. So who made Hubble? Well, the company is called Perkin-Elmer. It is a Connecticut optical company started in the 1930s to build amateur telescopes by a gentleman named Mr. Dick Perkin, and Mr. Elmer. Dick Perkin was a financier who worked on Wall Street. Uh, Elmer was a court reporter. Both of them were both amateur astronomers, and they met at a conference at Harvard University for amateur astronomers and decided in the late 1930s that it would be a good idea if we built some amateur telescopes here in the United States before the war that was imminent broke out in Europe. So they started the company in the late 30s and started building some amateur telescopes. Then the war broke out, and World War II pushed them into doing military optics. It wasn't where they started to go. They actually had tremendous success building reconnaissance systems. The most ambitious one of all was they built the CIA satellite cameras that flew in the 70s, primarily in the 70s, but they extended into the 1980s. NASA contracted Perkin-Elmer for 3 items. The first was the optical telescope assembly. This is the 2 mirrors that make up the telescope itself. The fine guidance sensor, which provides pointing information, tells the telescope which way to look, up, down, left, or right. And then finally, there was an optical control sensor, which was going to detect alignment errors on orbit. So if things got somewhat misaligned as the system was in function, they could try to make corrections as time went on. So in the way NASA runs their programs, a major program like the Hubble was under the supervision of Marshall Space Flight Center in Huntsville, Alabama. This is one of the several space flight centers that are scattered around the United States. So they were the awarding agency. The weird thing is Marshall is the rocket expert for NASA. They had no knowledge of optics or astronomy. And it took them months before they could find someone with an optical background to be our on-site engineer or representative for Marshall. Initially, ironically, NASA couldn't enter Perkin-Elmer's top secret facility where the Hubble would be built. They didn't have the security clearances that was necessary for people in that building. That building housed where we fabricated the CIA satellite cameras and had space simulators that we would later use to test the Hubble components. So many of you may never have ever heard of Perkin-Elmer, but they have a track record which I think is outstanding. I make these statements and they're going to seem outlandish initially, but in reality, I think they are very close to the truth. I'm saying that they prevented World War III. Back in the 1950s, we were living in fear of a nuclear holocaust. There was people running around building fallout shelters. There were bomb shelters located throughout the United States. There was a great fear that the Russians would have a sneak attack on the United States, not unlike what happened at Pearl Harbor. President Eisenhower insisted that the intelligence community find a way to find out what the Russians were doing. So they came up with this satellite cameras, which turned out to be tremendously successful. Those satellite cameras were then used when the United States and Russia negotiated a SALT agreement. This is a strategic arms limitation talk that they had. and allowed us to reduce the nuclear weapons that both countries were carrying. Also, the next statement is also very, very wild initially, that they made personal computers and cell phones possible. Back in the early 70s, the electronics industry realized that printed circuits would be a great way to enhance the industry, being able to reduce the size of circuits, reduce the power they needed. And it was just, a wonderful, wonderful thing that was going to be able to happen when they could make printed circuits. And the way they made them was they would draw up a circuit on a large board, probably 30 by 30 inches, and then photo reduce it down to a miniature less than an inch in size. This image was then contact printed on a piece of a silicon wafer that had been treated to make it photosensitive. It would then be processed and developed like a film would be processed, and out would come the circuit. The trouble was that every time they used this technique, the master got damaged. It got a little bit abused with each time, and they could only get about 10 circuits out of one master. And then they would have to start all over again. So the solution was very simple. People thought of it immediately, and that was have a projection system that would project the image onto the silicon wafer. Several people tried to make them. No one was successful. The Air Force came to Perkin-Elmer in 1974 and asked them if they could make a projection system. Took them about a year, but they came up with a system that worked, and it worked very, very well. No sooner had they got it working, then the industry came around and says, well, can you make it a 3-inch system to do 3-inch wafers? So it took them another year or so to come up with the 3-inch version, and that worked as well. Now, I'm going to use memory chips as sort of a gauge here because those are the most common chips that are made. So on the 3-inch circuit, on the 3-inch wafer, they could now squeeze 9 1-inch chips onto that 3-inch wafer. And the original ones maybe had a resolution or a memory capability of about 1,000 bytes. The new ones on the 3-inch wafer had 16,000 bytes. So there was an improvement or productivity improvement of 145 times. So obviously, it was a huge, huge boost in productivity. Soon after they started building a 5-inch system, then an 8-inch system, and I had a little minor role in the 12-inch system, which was being built about around 1990. I have no idea how far they've gone with that, because at that point in time, that part of the business was sold off by Perkin-Elmer. The other thing that they did was during World War II, one of the engineers, Dick Kinnaird, in fact, he was a neighbor of mine, he came up with the idea that we could build a thing called a photospectrometer. Now, they were too busy with the World War II work, and it was sort of put aside. But after the war, it was decided they would go build one. And at the same time, Dick Perkin asked a marketing research company whether there was a market for this instrument. And they came back and they said, well, we think maybe you could sell 8 totally throughout the next 10 years. They've sold not millions, but thousands and thousands of these instruments. Every major lab throughout the United States, in fact, out the world, has a Perkin-Elmer spectrophotometer, and they've built mass spectrometers and a whole series of other instruments. They are the leader in this industry, which sells billions of dollars of instruments every year. Now, Perkin-Elmer also built 3 of the 4 telescopes NASA wanted: the Hubble, Chandra, and the IR telescope. Now, we're going to talk a lot about the Hubble, but the Chandra, just give you a thought. The Chandra photographs X-rays. Now, how do you photograph an X-ray? Doesn't X-rays go through almost everything? So they came up with a way to record X-rays on film. So that was a challenging thing. CERTA also was a challenge. The primary mirror is made out of a material called beryllium. Beryllium is a wonderful material from an optical standpoint. It does a marvelous job of reflecting infrared energy. But beryllium, when you are machining it or working it, it produces a very, very poisonous substance from the beryllium that gets into the lungs, and it's almost like the lung diseases that are common. So we had to learn how to polish beryllium, and they polished it under a hood. So that worked, and it's worked very well. So why should we go up into space to study it? So we wanted to understand how stars and planets were formed, and we'll talk a lot about that. We're going to measure, they wanted to measure the size and the age of the universe. They wanted to test theories about the universe, and one big theory, of course, is the Big Bang. They wanted to investigate the existence of what we call large-scale structure. So what do I mean by that? Well, planets, they make up solar systems. Well, solar systems make up galaxies. Do galaxies make up something else? Well, the answer turns out to be yes. They make up what we call clusters. And is there another step beyond that? They're still looking at that. But they also wanted to be able to test some of the theories that we could not verify in a lab. So briefly, what are some of the things that they looked at? They looked at planets, stars, planetary nebula, and I'll skip that for now, galaxies, supernovas, and finally black holes. So looking at comparing a ground-based telescope and a space telescope, what are the advantages? So in the ground-based, you're limited by weather. Well, there's no weather in space. So you can only view the stars or the heavens at night on the ground, but up in space, you can look at them 24 hours a day, 7 days a week. Half the sky is only visible on any one point of the Earth, whereas the entire sky is visible from space. Ultraviolet light is blocked by the atmosphere, and we cannot see things in the ultraviolet, which you can see, of course, from space. Also, infrared objects are often masked by the warm Earth that's nearby. So you can see much better in the infrared in space. So who was Edwin Hubble? He was a University of Chicago student who excelled in all the sports, but he studied law per his father's wishes. He went on to become a Rhodes Scholar and studied at Oxford. And then after his father passed away, he took up his first love, which was astronomy, and earned a PhD in astronomy. So why is he important? Well, in 1925, when he was coming out of grad school, the Milky Way was considered the entire universe. There was nothing beyond the Milky Way. But he discovered galaxies, and galaxies were outside the Milky Way. He was using the new Mount Wilson 100-inch telescope to find these new galaxies. He is astronomy's Christopher Columbus. He also found that all the galaxies were moving away from us. And the further away they got, the faster they went. He came up with the explanation, which was correct, that the universe was expanding. This resulted in what we now call the Big Bang Theory, that everything started from a single point and has been expanding ever since. So let's go to the telescope that was used for the Hubble. The telescope design is what we call a Ritchie-Chrétien. It was originally invented or discovered in the 1910s by two people independent of one another. Ritchie, an American, and Chrétien, a Frenchman, came up with the ideas, and they are two mirrors that are hyperbolic in shape. They produce really great imagery, but are very difficult to build and test. So how do you test a hyperbolic mirror? Well, we came up with this concept back in the 60s, long before Hubble, by the way, of using what we call a null lens. The null lens actually takes a point image and distorts it so that when it bounces off the aspheric mirror that we're testing, it comes back through the system and reproduces another point. So we get rid of the aberrations that the aspheric mirror has introduced. We null them out. So we were trying to demonstrate to NASA not only the null lens, which had been around and functioning for many years, but we were also trying to demonstrate that we wanted to polish the Hubble mirror via computer. And to do that, we bought and fabricated a 60-inch mirror, which we called a demo, showing them exactly how it would work. And then we proceeded to go ahead and use that technology on the Hubble. Between the two mirrors, we had to reposition the field lens in the null lens assembly. Now, you have to imagine this is not a very simple task to do. In the test chamber, which was located where the mirror was being tested, the null lens is about 30 to 40 feet in the air, built on top of the chamber, with a very, very difficult access to it. And the technicians were working literally blind. They were looking at a TV camera mounted next to the null lens and adjusting the null lens position using the TV camera. So they couldn't really see exactly what they were doing, but they could just see what the TV camera was showing them. And they were convinced that they had adjusted the null lens correctly. But as we will later learn, they did not. So quickly, here is Dr. Marty Yellen watching the grinding operation going on the primary. You can see the top of the mirror is a disc. In the next image, Davy and George are inspecting the surface, looking for any surface defects. And you can see how the mirror was built. The mirror is built on, they take a lattice work of strips of material and sandwich or connect them together in what we call a honeycomb. And then there's a top plate and a bottom plate. Now, all of this material looks like glass, but in reality, it is a ceramic. It is made by Corning Glass Works up in Ithaca, New York. And the tremendous thing about this mirror and why it's made the way it is for its coefficient of thermal expansion. It has a design goal of reaching 0, which very few, almost no materials have a 0 coefficient of expansion. And it has a tolerance on that 0 of 1.5 times 10 to the minus 9. Now, Corning also invented a material called Pyrex, and many of you are familiar with it and use it in cooking. But you may not know that its main contribution in the late 40s was being used for the 200-inch mirror at Mount Palomar. Unfortunately, they were cooling it off a little too quickly in New York State when it cracked. It cracked because they did not anneal it at a slow enough pace. So they had to make a second one, and that is the mirror which is in Mount Palomar. And it too has a low coefficient of thermal expansion, but certainly not 0. And the reason why this is important is because if the mirror changes temperature, it will change its focus. Its focal length will change dynamically with temperature. So it's very important to try and keep the expansion coefficient as low as possible. So when it comes to testing these mirrors, it turns out that the air that we breathe will distort the imagery that we're trying to see through to see how the mirror is doing. So what we do is we put these mirrors into a huge chamber, which we can evacuate. It's a vacuum chamber. And we literally float the entire chamber on a column of air in order to minimize vibrations coming through and upsetting the test of the mirror. Gravity also distorts the mirror. Now remember that the mirror is going in space and it's going into an orbit around the Earth where there is no gravity. It is absolutely 0 gravity or 0 force of gravity on the mirror. But the gravity here on Earth in a testing environment would bend the mirror a huge amount. We came up with a mount which is called the bed of nails mount. And like in the illustration in the right, where the balloon is sitting on a bunch of sharp points, each point is supporting a very, very small amount of force into that balloon, and therefore the balloon does not break. And likewise, on the mirror, we had, I think it was 247 points that supported the mirror while it was being tested, keeping the mirror essentially in a gravity-free environment. So there was no end-to-end test where the mirrors were put together and we tested from end to end. The reason for that is pretty simple. In order to do a test like that, we would have needed a very large optical flap, which are very difficult to make, and there was none available that anyone knew of, and it would have all the same problems of supporting it in a gravity-free environment and in a vacuum. So the components were then tested independently, but We had proposed an end-to-end test, but as I described, that test was rejected by NASA due to the cost and schedule impact. The ironic part of this whole thing is that Hubble was on the launch pad, getting ready to go off, when the Challenger was actually launched and it blew up. That stopped the whole shuttle program and immediately put the program on hold. Hubble was stored for 4 years at a cost of $8 million a month, while the whole shuttle program was re-examined and tried to fix any of the problems that might have been around. Certainly there was time enough to fix any problems that would have occurred or that we would have found with the Hubble. So in 1990, we finally got it into space, and the first images came back. They were fuzzy. It was a slow news day, and the news media just went wild. They were howling about how we had spent millions of dollars and got this big thing up in the sky, and it doesn't work. No one seemed like they wanted to know what you could do about it. They just simply, were mocking NASA about what a terrible thing this was. Meanwhile, NASA went literally into hiding. They wouldn't even answer their phones during this period of time. So in reality, it was the Null lens that caused the problem, and the mirror came out actually with a very near perfect curve, but the wrong curve. What they could do, it turned out, is they could take bright images and use a computer algorithm and actually correct the images, make them as good as they could have been. Faint images, however, didn't work. The reason being there was not enough energy being concentrated into a small enough point for the detectors to sense. So what was done was the experiments for the Hubble were just simply rearranged. Any experiment that involved bright images were moved to the head of the line and done first. The net result was no viewing time was lost. Excuse me. So what happened was we were able to fix Hubble in space. We used what is called CoStar, which was a simple optical corrector that was placed in one of the instrument packages. And it was brought up in 1993 during the first service mission. Now, most people thought, my God, that's the first thing they got to do is get up there and fix that image. But in reality, it was not. There were some gyros built by Lockheed that had been failing. And they were failing to the point where if one more failed, the telescope would have been out of control. They would no longer be able to point the telescope. So that was vital that they change out those gyros. Secondly, the solar panels had an issue. The telescope is going around the Earth every 97 minutes. Half the time it's in the sunlight, and half the time it's in the shadow of the Earth. And every time it transitioned, the solar panels shook the telescope. And literally no viewing could take place for several minutes after each transition. So the second thing that they had, the astronauts had to do was to change out the solar panels. Finally, they did put in the CoStar, and on subsequent service missions, missions 2, 3, and 4, when new instruments were installed, they had the correction built in, and it worked beautifully. So here's a quick snapshot of the fine guidance sensor, which was my joy of work. And this device this is a cartoon, by the way. It's not anywhere near scale or accurately showing. This particular unit has what we call cloister prisms, which are angle sensing prisms. So one pair of prisms senses left to right motion, and the other pair of prisms senses up and down motion. They have very, very limited range, but they're very sensitive. They're extremely sensitive. The interesting thing about these prisms is you can see in the diagram, there's a dividing line between them. The two halves are what we call optically connected. There is physically nothing between them holding them together. The way these are built is the optician polishes the surfaces on both halves so smooth and flat that he can squeeze the air out between the two prisms, and they literally combine or contact one another with doing molecular to molecular attraction. It's a phenomenon that's been used in optical shops probably for 100 years, but it's been a long-term thing that optical shops have used for, as I said, 100 years probably, in making various optical components. Now, these have been up there these have been together for about 40 years, and we don't think they're coming apart anytime soon. So NASA gave us a catalog of guide stars that we had to use to keep the telescope pointing correctly. And what the fine guidance sensor would do is it would find one of these guide stars and measure the angle of the telescope to that star. And it would report that to the gyro systems, which would correct the telescope and bring it back in alignment. Many of the people that came to review what we were doing said, "Oh, this is never going to work. This is too complicated. It's just not going to do it." There are 4 fine guidance systems that were built. 3 are active in space at any one time. The 4th one is a spare on Earth and is used to as a replacement, and so they can rebuild one of the other units while the unit is in space. NASA's specification to us was that we had to hold the pointing. The pointing error could not exceed 7 thousandths of an arc second in 24 hours. Now, you can look at the best survey equipment on Earth, and it can only measure down to, and this is iffy, 1/10 of an arc second. The Hubble itself can resolve 0.05 arc seconds. The worst FGS, and they're a little different, each one's a little bit unique. The worst one is 4 thousandths of an arc second, roughly half the tolerance that we had. And the best one got all the way down to 1 thousandths of an arc second. So it was an unexpected bonus that there were 3 guidance systems on the telescope, because 2 were only needed to lock in the telescope pointing. The 3rd one was literally going to be idle. But it was pointed out to NASA that, hey, You can use that third fine guidance system to make some astronomy measurements. You can measure the separation of stars. And one of the big stars that they wanted to measure were binary. It turns out that 85% of all the stars in the universe are binaries. And the fine guidance sensor could find these and measure how far apart these two stars that are orbiting one another are apart. It was an unplanned activity. NASA never realized until after the contract was well underway. So here's some Hubble telescope pictures. This is from the what we call WIFPIC. This is the Wide Field Planetary Camera 2. This is the second version. So it's after the correction had been put in 93. And it shows Mars separated in time by about 2 months. And in the first one is a nice clear picture of the planet. On the second one, the planet is covered in dust. There's a dust storm that covers the entire planet. So here's Jupiter in a Hubble photo, illustrating or making a good image of what we call the red spot. And Galileo in 1609 was the first one to see the spot with one of the first telescopes ever built. So that spot is a storm on the surface of Jupiter, and it's over 400 years old and doesn't seem like it's going to change anytime soon. Here's Saturn taken with 3 different portions of the spectrum: ultraviolet, visible, and infrared. And they gather different information from each of these different photographs. So how do they take photos? Well, it turns out that we only take black and white photos, but we use a filter and take 3 identical pictures with 3 different colored filters. When the images are processed here on Earth, the colors are added back in, and you get colored images. So I'm trying to illustrate how satellites work. I'm using a cannonball as an example. Not a very practical example, but I think you'll get the picture. If you shoot a cannonball off parallel to the surface of the Earth, gravity is going to pull it down and it's going to hit the Earth. By shooting the cannonball faster, it goes further around the Earth, as it shows in the second illustration. If you pick just the right speed, the cannonball never touches the Earth, but keeps on going at a constant distance above the Earth. If you use too much speed, the cannonball leaves Earth's gravity field and will never return. So, knowing that there is no orientation, the cannonball can be pointed in any direction so long as it's parallel to the surface of the Earth. It doesn't have to be over the poles or the equator. It could be anywhere. But look at what happened when they realized that the planets are all in one plane. Nobody at first knew or could understand why they were all grouped together in the single plane. From a physics standpoint, there was no need for that. So this goes on to explain how the universe, or how the planets, the solar system, were formed. So first thing you gotta know is that the space out there is not empty. It has a lot of atoms and molecules running around, in clouds. They're not very dense, but they are there. They're the remnants of planets, stars, and entire galaxies that have been out there. So this is called the creations of time. It's a very famous Hubble picture. So what happens is one of these clouds starts to collapse. They're not sure why. Supernovas have been suggested as a possible cause, that the supernova impact starts the cloud to collapse. But basically what happens is the molecules, the atoms and the molecules collide, and they stick together. They collect, they coagulate. And by doing so, they are creating gravity. The more of them collect, the more gravity it is. And at the same time, they also generate heat. The collision is energy. And when the energy is absorbed, it comes out as heat. So the gravity pulls the cloud towards the center. And the cloud has roughly a spherical shape. So the top and bottom of this cloud collapse. They start moving towards the middle. But centrifugal force, because the cloud's rotating, keeps the middle expanded. It never collapses in the middle. The cloud flattens. It becomes a disk. So a disk gets formed, and as it becomes smaller, it spins faster. And just like the spinning ice skater, as they pull in their arms, their spins pick up speed. And that's what happens here in this disk. It's the conservation of angular momentum. Gravity is pulling most of the material to the center, and it forms what we call a protostar. The colliding material is producing heat. The heat will cause the hydrogen to fuse, creating a nuclear reaction, and a star is born. Surprisingly, only 0.2% of the remaining material is used to make all the planets. So, sort of repeating this, at 10 million degrees, the colliding hydrogen atoms will fuse into helium, creating a new element. The helium with less mass is going to release energy, according to Einstein's famous E=mc². So that little tiny bit of mass that the helium atom gives up creates the energy which provides us with sunlight and heat. So you might ask yourself, well, if you created a new element by fusing two hydrogen atoms, can you create other elements in this manner? And the answer is yes, but you need a bigger star. You need more fuel to get more collisions and to get faster and higher temperatures. So all the elements from hydrogen to iron are created in this manner. It turns out that you need to have a supernova, which has huge amounts of energy, to create the speeds and the temperatures needed to make the remaining elements of the periodic table. So the Hubble confirms this whole theory. In the top of the slide, we have photographs from Hubble, and down in the lower part, we have what the artist version of those same photos, making it a little clearer to see what was going on. And you can see that they are forming disks, with the center of the disk igniting into a nuclear reaction. And I love this slide. This slide shows the complete evolution of a star. Starting in the far right-hand side, the star goes nuclear and emerges from this violent start as our star, like our sun, and continues life seemingly unchanged for billions of years, literally billions of years. But near the end of its life, the sun, or the star in this case, starts to expand. As the fuel gets burned out, it starts to expand. And it becomes what we call a giant, a red giant. But after a period of time, that whole giant collapses, implodes, creating what we call planetary nebula. And at the center of that planetary nebula is a white dwarf, which is the remnants of the star. So someone asked me one time, why are planets round? Well, you got to remember that when the planets are formed, they are really mostly hot gases. Certainly Jupiter and Saturn are all gases, but the inner planets will cool off and become liquid, and then finally a solid. And as the gases cool, the hydrostatic forces form a ball. The gravity wants to pull them all together into the center, but the thermal temperature is pushing them out, trying to keep them apart. So the materials in these, as they solidify, stratify. Heavy materials like iron sinks to the center, and then the lighter materials floats on top. Continents are actually considered light by this standard, and they float on top of our hot liquid mantle while we have an iron core. So here's a quick snapshot of the planets where the sizes are approximately. The spacing is certainly not the right spacing for these planets. And you'll notice that Pluto is not in the group. Why not? Well, here's a little diagram showing why Pluto is not there. Pluto's not part of the original disk. It was formed somehow the way other than through the process I just described. So astronomers back a few years ago came up with a set of rules that planets must have in order to be considered a planet. They must orbit the sun, they must be a ball shape, and they must clear the neighborhood. Well, what does clear the neighborhood mean? Okay. When they form into a ball, there's a lot of debris around them. And that debris needs to be cleaned up, pulled together, pulled down, and cleared away from their path. And so they decided that Pluto was not eligible to meet that criteria. And for good reason. If you look at some of the larger dwarf planets, Pluto's not even the largest one. Eris is. So there are other planets or other dwarf planets which are larger than Pluto. And there are a number of them which are pretty close. So we had to cut it off someplace, and there it is. So sort of reviewing the solar disk, which creates the planets, So solar disks create planets, but there are also a planet disk, which creates moons. And now currently we have Jupiter has about 69 moons, Saturn 62, Uranus 27, and Neptune 14. Now, Earth and Mars both have moons, but they're very, very different. And we'll get into that in the next slide or two. But the solar disks, they're very, very common. We believe lots and lots of planets are out there. The Milky Way galaxy has over 400 billion stars, and there are about 200 billion galaxies. So there was a satellite that we sent up a few years back, which set out to look for planets. And as of September of 2016, they found over 3,500. There have been more discovered since then, but that particular system was shut down at that time due to some problems that were going on. And a replacement has gone up. So what about the good old moon that we have? Well, look at the size of our moon relative to the size of the Earth. The moon is 27% the size of our Earth. Look at Jupiter's largest moon. It's less than 4% of the size of Jupiter. And Ganymede is over twice the size of our moon. So how'd that happen? Well, although nobody was here to record it, we think what happened was the Earth was smashed by a large object while it was still in a molten shape 4.5 billion years ago. And that collision splashed out the moon. The moon was located very close to the Earth, with the Earth rotating rapidly, and had a 5-hour total daylight. So it wasn't 24 hours days, they were 5-hour days. So what happens is, as the ocean tides will slow the Earth's rotation. And when it does, it causes the moon to recede away from the Earth. And eventually it will create what we call tidal lock. At some point in time, millions of years from now, the moon will no longer rotate around the Earth, which it does every 28 days. It's that part slowing as well. It will eventually get to the point where it will be located fixed over one part of the Earth. Mars, again, another little quirky thing, is right next to the asteroid belt, where there are thousands of objects that are flying around, and objects are bouncing off one another. And we think that 2 small objects came out of the asteroid belt so close to Mars that they were captured in Mars's gravity field and became moons of Mars. So what's going to happen with the Hubble? Well, when the Hubble was last visited in it was probably 2009. It's been on its own. It has not been serviced since, because we retired the space shuttle, which was our only vehicle we had that could get to it. We no longer have a vehicle that could get there. So what's going to happen is eventually, as it gets close to the atmosphere, it will slow down and will eventually crash into the Earth sometime way in the future. Meanwhile, what's coming next? Well, there is a new telescope coming called the James Webb Space Telescope. And as you can see in this illustration, it's much larger than the Hubble. The Hubble mirror is roughly 8 feet in diameter, and this is about 24 feet or so in diameter. So in space, we were able to save the day by repairing the telescope from a design flaw that had occurred and nobody was aware of. So we rescued the telescope and made it in what some people have described as the greatest scientific tool of the century. One of the things which I have been fascinated by is that with each service mission, we've been able to replace the cameras with better and better cameras. And the imagery that we've been getting has improved steadily. The Webb telescope, however, will not be in an orbit that we can get to. The telescope will be located approximately 1 million miles from Earth in Earth orbit. It will be you can either think of it as trailing Earth or leading Earth, but it's going to be located 1 million miles away, and we will not be able to get to it to repair it or to do any upgrades. So we are now at the Q&A. If you move your mouse and click on the hand that appears near the bottom of your screen, you will be able to ask a question. In preparation for this, I've prepared 2 questions, which I'll answer right now, and to give you time to think about other questions you might want to ask. So the first question I'm going to address will be the Webb telescope and how it will be used. The Webb telescope is an infrared telescope. It will not have the ability to get visual or, excuse me, visible images. And you may wonder why that is. Well, there are a couple of reasons. First reason came out of a thing called Star Wars. Back in the 80s and 90s, the military had this wonderful idea that we'd be able to shoot down incoming ballistic missiles with a laser. And when it was tried, they found out that the atmosphere disturbed the beam so much that there was not enough energy focused on the incoming ballistic missile to damage it. So somebody came up with the brilliant idea that rather than try to get the power up there to fire away at the missile, why not distort the beam going up so the atmosphere restores the beam to its original quality, and you'll now have enough energy to damage the missile. It was tried and it worked. It's still, as far as I know, not in use, but it became a great idea for people who wanted to build visible telescopes, because now they could take and shape the telescope mirrors to contradict the distortion the air created on the imagery. Thus led to what we call deformable mirrors. And they actively measure what the atmosphere is doing and deform the mirror to correct for the distortions that the air is introducing. Thus, it made it practical to build very high performance telescopes here on Earth in the visible portion of the spectrum. The other reason, or one of the other reasons, is As I pointed out, Hubble discovered that the stars in the galaxies that were moving away from us the spectrum was being shifted into the infrared. Well, as you get further and further away, these stars are moving faster and faster, and the shift is getting greater and greater. So the energy coming from these stars is moving into the infrared. And so the work that's proceeding for most astronomers is on what's happening near the edge of the Big Bang, which is out there 13 billion years out, light years out. And those images are coming back greatly shifted into the infrared. So the telescope was designed to work in that spectrum. Now, and of course, the other big problem with space-based telescopes was the cost. They were very expensive. Now, why did Perkin-Elmer get the Hubble contract? And who else could have done the job? Well, it turns out that the satellite program, the reconnaissance program that Perkin-Elmer got from the CIA, actually helped them get the Hubble contract. They had the test equipment needed to test some of the Hubble components. They could do that from the original contract from the CIA because it was no longer being used. It was just literally scrap work that was left. Even though it functioned well and everything was working fine, they used those giant space simulators to actually test the components of the Hubble. So it gave Perkin-Elmer a financial edge up on the competition. Well, who was the competition? Turned out it was a place called Eastman Kodak. You may have heard their name. And they partnered with another company who was competing with Perkin-Elmer on a number of systems called iTech. And they actually got a part of the contract for the Hubble. They were contracted by NASA to build a backup primary mirror. And they were well along in that fabrication process when NASA realized that the Perkin-Elmer mirror was coming out and looking to be as if it was going to be the best mirror that had ever been built. And they stopped the contract with Kodak. So they were the ones who could have done the job as well.
Ken, what's the next step in the telescopes as we continue to move further out with spacecraft that are going further out in the universe? Will telescopes be necessary, or will we simply be there ourselves, and so hence we do not need a telescope?
Great question, Mike. Now that we will still always have and will still always want to use telescopes. Telescopes are instruments to allow us to see how things are becoming. The telescopes often have spectrometers in them, which is what we talked about it earlier in this presentation. And they allow us to see what the composition is of stars. And you can only do that with a telescope. So I see that telescopes will always be with us, and it will always provide us with a means of investigating what's going on in the universe. And I never see a place where that will ever end.